this tape segment we're going to describe the optical properties of anisotropic minerals using orthoscopic view. And we're going to show how to use these properties for identification of specific minerals. So I want to run through a list of optical properties that you can measure in orthoscopic view. And then in our next segment we will begin to look at conoscopic view with mineral grains, which enables us to describe other properties. So the first property I want to discuss is the property of color. And we've demonstrated this before using the mineral tourmaline, which is a nice uniaxial mineral. The color of a mineral results when certain wavelengths of white light are absorbed. And color is a complex property for anisotropic minerals. In fact, as we look at tourmaline again and demonstrating the color of tourmaline in plane polarized light, you can see that the color is dependent upon the orientation of the tourmaline with respect to the microscope polarizer. When color becomes complexly associated with orientation, we don't call it color anymore, we call it pleochrysm. And uniaxial minerals have a special form of pleochrysm which we call dichroism, which indicates that there really are two kinds of end member colors that describe the pleochrysm in uniaxial minerals. In biaxial minerals, we have to consider more than two kinds of colors, and we'll talk more about that later. Now, another thing we can see with tourmaline, and I'll just move to a different orientation of tourmaline, and this is the form of the crystal. Now, among uniaxial minerals, there are two kinds of crystal classes that we need to consider, the tetragonal and hexagonal crystal classes. And it's quite clear from looking at the tourmaline that it's a hexagonal mineral. You can see the hexagonal form of the tourmaline in these C-axis sections, these sections where the C-axis is perpendicular. You can see the hexagonal prismatic kind of form that tourmaline exhibits. So that we need to look for expressions of form for each mineral unknown, because these can offer us information about its identification in the same way as color or pleochrysm is. Now, another aspect, another way in which the symmetry of the mineral is expressed is by cleavage. And I want to show you another anisotropic mineral. This is a thin section of a pyroxenite, and we're looking at the pyroxenite now in plane polarized light. And the pyroxenite, of course, contains large amounts of pyroxene. And looking at the pyroxene grains, we can see really two kinds of pattern of cleavage. One kind of pattern occurs in grains that are more or less elongate in this rock and consists of one cleavage form, all parallel to each other. I'm pointing this out on this particular mineral grain. And another kind of orientation shows two intersecting cleavage forms, as exemplified by this particular grain. This kind of cleavage is a prismatic cleavage, and with pyroxenes and amphiboles in particular, we pay a lot of attention to the angle of intersection between the two cleavage forms when we can see the two prismatic cleavages intersecting. You can measure this angle with your stage by rotating the stage from having it parallel to the crosshair in one for one of the cleavage forms, and then moving the stage around until the other cleavage form is parallel to the crosshair, as I'm demonstrating for you now. So this angular relationship in this particular case is very close to 90 degrees, is diagnostic of a pyroxene, and certainly serves to distinguish it from another common similar appearing mineral, the amphibole group. Well, there are other patterns of cleavage, and in order to show this, I'd like to give you a thin section which contains biotite. Biotite has a very well-developed basal cleavage. And here we're looking at a biotite grain where the basal cleavage form is very well shown. The platy form of the biotite mineral induces what we call a basal cleavage. This is a cleavage that is perpendicular to the c-axis and is extremely well developed in, well, all the micas, biotite in this particular kind of example. Now another kind of cleavage that is particularly important in uniaxial minerals is shown by the mineral calcite. And so I've got another thin section which shows the rhombohedral cleavage of the calcite, and a very similar kind of cleavage is shown by other carbonate minerals. It's characteristic of carbonates. And you can see this very well-developed rhombohedral kind of form, and anytime you break up calcite, it will break along these rhombohedral cleavage traces. And so this is a diagnostic cleavage form that occurs for carbonate kinds of phases. Well, the next property I want to call your attention to is relief. Now, the relief of a anisotropic mineral cannot be measured in the same way as we can for isometric ones. That is, we can't simply take a random grain mount and put it on the stage of the microscope and look for the Becky line in any orientation. Instead, we have to know whether we're looking at the ordinary ray or the extraordinary ray in the case of uniaxial minerals. And we can't do this in orthoscopic view. This is one of the main advantages that conoscopic view gives us. And that's something we'll be talking about next time. Evaluating relief of anisotropic, in particular uniaxial minerals, we'll speak about in the next tape segment. Well, if we can't evaluate relief, we can make a very good estimate in orthoscopic view of the birefringence of a particular mineral. And the way we do this is by application of a review of this formula which we looked at last time, in which the retardation is equal to the birefringence times the thickness. Now, it's possible for us to estimate with very good precision the retardation that a particular mineral grain is showing. And we do this by looking at the interference color which the mount or the particular mineral grain shows. And if we then have an estimate of the thickness of our mount, it's possible for us to also infer the birefringence of the mineral in that particular orientation. Remember that the birefringence is an expression of the difference, the absolute value of the difference between the two indices of refraction of the plane polarized components. And so by paying attention to retardation, then we can make an estimate of the mineral's birefringence if we know something about the thickness of the mount as well. Now, the way in which we calibrate this estimate is by using the Michel-Levy chart. And this is the Michel-Levy chart, again, which shows a pattern of interference colors. And if we're looking at a particular mineral grain and we can recognize one of these interference colors, for example, this yellow right in here, which is a second order yellow, if we can be sure that the mineral grain is exhibiting this particular color, then we know that the retardation is approximately 900 nanometers. And if we observe this color and we know something about the thickness, for example, here's the thin section thickness marked here at 0.03, then it's possible for us to, by solution of the equation delta equals B times T, we can make a direct solution of the birefringence of a particular mineral grain. Now I'm going to illustrate how we do this with some mineral mounts. So let me go back to the microscope now, and I'll place on the microscope stage a mount of a orthoquartzite sandstone. This is a sandstone seen in thin section, so that the thickness of the thin section is known to be on the order of 0.03 millimeters. And the rock is made up virtually entirely of quartz grains. And I'm looking at the mount now in crossed polarized light, and so we're looking at interference colors on these quartz. You can see them going to extinction every 90 degrees, each of these quartz grains. And I want you to notice that the interference colors on these quartz grains vary from a gray color on up to a creamy white sort of color. And indeed, the maximum interference color that we see for quartz is in that creamy white region. This is an indication of a retardation of less than about 200 nanometers. And given the thickness of the mineral thin section, we can infer then the birefringence of quartz as approximately 0.01 birefringence. So this is a low birefringence, as exemplified by the mineral quartz and estimated by the interference color. Now I'm going to switch mounts to a mount of olivine. And this is a rock dunite, which is made up virtually entirely of olivine. Olivine has a much higher birefringence, and here you can see the second and third order interference colors shown by the much more highly birefringent olivine grains. And these would be farther to the right on the Michel-Levy chart, and again, given the thickness of a particular thin section, would give you the possibility of estimating the birefringence of this particular olivine as being in excess of 0.03. So now let's move to a thin section of a marble. And marble is made up virtually entirely of carbonate, and the carbonate minerals have a very, very high birefringence. Here again, looking in cross-polarized light, you can see that the birefringence of calcite results in very high order interference colors. They appear almost iridescent, and you can also see some complex twinning within the calcite grains. These very high order interference colors are indicative of a very large retardation and a very high birefringence. The birefringence of calcite is greater than 0.1. And this is an example then of extremely high birefringence. So we've used then the interference color as observed in thin section as an estimate of the birefringence of particular mineral grains. Now the next property I want to talk about is extinction. Extinction is a phenomenon which occurs, of course, every 4 times in rotation with every anisotropic mineral. But there are different kinds of extinction when the extinction can be compared with some reference position on the mineral. A reference position related to its crystallographic form, as expressed by direct crystallographic shape of the mineral, or by cleavage. And so I'm going to give you some examples of different types of extinction. And we'll move to another mount. This one, a mount of some elongate minerals. And here we are looking at these minerals now in plain polarized light, and I'll cross the polars, and you can see that they show very nice interference colors, and they move to extinction 4 times during rotation. But I'm going to indicate the position of the crosshairs on the field of view here, and I want you to notice when extinction occurs in these crystals compared to the orientation of the crosshairs. And as I indicate right now here, the grain is going to extinction, and it goes to extinction at a time when it is precisely parallel to the crosshairs. This kind of extinction is called parallel extinction. And a great many uniaxial minerals are elongate and show parallel extinction. And so parallel extinction is an important property of an individual mineral. You should be able to recognize that the mineral grain goes to extinction when it is parallel to the crosshairs. Well, I'm going to go back to this rhombohedral calcite to demonstrate another form of extinction. Here are the calcite grains now. We're looking at them again in cross-polarized light, and I'll put the crosshair reference position on the screen again. And I want you to notice that the calcite rhombs are at extinction at a time when the rhombohedral angles on the edges of these forms are exactly bisected by the crosshair. Okay, this kind of extinction is called symmetrical extinction. And calcite, and indeed many minerals which have prismatic cleavage, show symmetrical kinds of extinction. So symmetrical extinction is a property which you should be able to recognize readily again in orthoscopic view looking at cross polars. Finally, there's one other kind of extinction which I'll point out to you, which occurs in another mount that I have here. Again, it's an elongate mineral, and again I'll rotate the mineral grain so that it goes to extinction and put the crosshairs in the field of view for you to, as a reference point. Again, I want to point out here that this particular mineral goes to extinction at an angle to the crosshair, when the elongation of the mineral is at an angle to the crosshair. This kind of extinction is called inclined extinction. And many minerals, especially those in the less symmetrical crystal classes like monoclinic and triclinic crystal classes, show inclined extinction. Now it's possible, using the microscope setup and using the orientation of the stage, it's actually possible to measure an extinction angle. For example, if I position the microscope like this and the mineral grain is located in one particular reference position, I can rotate the stage and I can actually measure the angle using the graduations on the stage here between extinction and the elongation of the mineral. And so that inclined extinction is a bit more complex than the other properties, because often we want to measure the angle of inclination between extinction and elongation of the mineral. And if we need to measure that angle, we can use again the graduations on the stage itself in order to measure this angle. Well, the next thing I want to do is to demonstrate the use of accessory plates. And just to refresh your memory about accessory plates, we have actually three kinds of accessory plates. We have the gypsum plate and the mica plate, which look very, very similar. They have symbols on them, these particular ones, which show the direction of the slow ray. That's an important thing to take account of. This is the slow ray direction. It happens to go across these particular things. And they also have symbols which show lambda and lambda over 4. Now these symbols refer to the amount of retardation in which these accessory plates supply, because that's the purpose of the accessory plate. That is, it is to impose a specific value of retardation on the field of view. Now, expressed in absolute amounts, the retardation that's imposed by a mica plate as exactly 145 nanometers. If you put a mica plate into the field of view without any other mineral grains, what you will see is a weak first order white interference color that will be imparted because mica of that particular thickness gives you a retardation of 145 nanometers. The gypsum plate has a retardation where the 1 lambda refers to the middle really of the visible light spectrum, or a retardation of 550 nanometers. And the interference color that you observe then with a gypsum plate in by itself is a second order red interference color, 550 nanometer red interference color. Now the quartz wedge, the third kind of accessory plate that we have, has a variable value of retardation, and I'll be talking a bit more in detail about the quartz wedge and its use a little later on in this segment. But first then I want to demonstrate the use of these two accessory plates. So I'm going to go back to the thin section of the orthoquartzite. Now, the orthoquartzite, put it back on the microscope stage, and we'll look at the orthoquartzite now in cross-polarized light. And again, you see the nice first-order white interference colors that are imparted by the mineral quartz. The maximum interference color, again, is this creamy white sort of color. So the first thing I want to do is to single out a particular quartz grain here, and we'll look at the insertion of the mica plate. The mica plate going into the accessory slot, and now it's in the accessory slot, and now I'll take it back out again. Now you can see that the interference colors of these quartz grains are now changed by the insertion of the mica plate. And now we see some of the quartz grains that have distinctly yellow and orange interference colors. That is, a higher degree of retardation is imposed. Those grains which have a higher interference color at any particular angle of rotation are those grains whose slow rays are parallel to the slow rays in the accessory plate. Now, in order to show this, I'm going to actually rotate the microscope so that it has the orientation that it does for you in the when you're normally using it. Okay, and we talk about north-south being in this direction. We talk about east-west direction going across the field of view like this. Well, the accessory plate goes in a slot in this kind of orientation, like this, into the plane of the microscope. That is, being inserted in this direction. And the slow ray in the accessory plate, this particular one, is across the accessory plate. This means that the slow ray in the accessory plate, we know, in this particular case, has this orientation. And so for those quartz grains in the thin section that now show higher order interference colors, we know that their slow ray direction is parallel to the slow ray in the accessory plate. So the mica plate then we can use as a tool for locating the slow ray in any kind of a mount, thin section or immersion oil mount. Now let me do the same thing with the same mount using a gypsum plate. Now the gypsum plate goes again in the same kind of slot. The slow ray orientation is the same for the gypsum plate. And as we look at the mineral mount now, the thin section mount of the sandstone, you can see that the colors have changed very radically. The colors that we now observe on the quartz grains are much higher order. We see many blues, we see many yellow interference colors. And the Blue, the grains which look blue now are the grains in which the slow ray of the quartz is parallel to the slow ray of the gypsum plate. The grains, and see as I rotate the stage, these interference colors will change, and that's because, of course, the slow rays are rotating. Slow and fast ray, their angular relationships are rotating. So individual grains change their interference colors depending on whether the slow ray is parallel or opposite to the slow ray in the accessory plate. The blue grains then represent those grains which have slow rays parallel to the gypsum plate. The yellow grains represent those grains which have slow rays opposite to the gypsum plate. Okay, well let's stop for a second now. We'll go back and look again at the Michel-Levy chart to see how this accessory plate affects the retardation in a particular case. Now the quartz normally has a maximum retardation that's shown right here in the diagram. Couple hundred, 150 to 200 nanometers typically. Now if we use the mica plate, the maximum interference color will be increased by about another 150 nanometers. So we'll move over in this direction to this kind of a color. So those grains with their slow rays parallel to the slow rays in the mica plate will have maximum interference colors now in this particular kind of region. Now, when we use the gypsum plate, the addition is substantially greater. It's an addition now of 500 nanometers, and it moves the first order white quartz color clear on over here into this blue color band in the second order region. So we've imposed a very much larger interference color variation on, and these grains now show a second order blue interference color. For the grains which have actually opposed the gypsum plate, there is a subtraction, and we subtract out the 150 nanometers, but the gypsum plate imposes an even larger retardation, which moves us back up the interference color to this yellow. So we see either a yellow color or a blue color depending on whether the retardation is enhanced by the accessory plate or whether it's working opposite to the accessory plate. Okay, now we can combine the information about the position of the slow ray of the mineral with information about the crystallographic form of the mineral. And let me demonstrate how we do this. This is measuring a property, for example, called elongation of the mineral. Now, elongation really relates to the position of the slow ray relative to the shape of the mineral. And the basic nature of the test I can show on this mineral mount again, which I used for the purpose of parallel extinction. It's an elongate mineral which goes to extinction when it is parallel to the crosshairs. Now I'm going to rotate that mineral grain to such a position that it shows maximum illumination. Now maximum illumination occurs at a position 45 degrees from extinction. And since this mineral grain has parallel extinction, maximum illumination occurs when the mineral grain is at a 45-degree angle to the crosshairs, which you can see in this particular mount. Furthermore, I've fixed this mineral grain so that it is elongate toward the northeast. And this northeasterly direction is precisely the direction of the slow ray, which occurs on my accessory plate when I insert it. So I want you to observe the interference color, which again is a similar first order white interference color, and I want you to notice what happens to the interference color when the gypsum plate is introduced. Okay, now I'm introducing the gypsum plate into the accessory slot of the microscope, and you can see that the interference color changes from a white now, again, to that second order blue color. That indicates that the mineral has its slow ray parallel to its elongation. This means that the mineral has, by convention, what we call positive elongation. Positive elongation, or else we might say that the mineral is length slow. Okay? Now the opposite sort of situation I can show you in another mineral grain. I have another mineral mount here of an elongate mineral, just to show you that the opposite sort of situation can occur. And again, introducing, it has parallel extinction again, which you can observe just in cross-polarized light, and inserting the accessory plate, you can see that the interference color now is a yellow rather than a blue color. That indicates subtraction. It tells me that the slow ray is perpendicular to the length of the mineral. This mineral has a negative elongation, we say, or perhaps we would describe it as length fast. Both kinds of notation are used. Okay, just a summary then of this determination of elongation shown by this diagram. Here's our accessory plate, which is inserted in the microscope in such a way that we know the position of the slow ray, and if the colors add when the elongate mineral is parallel to the direction of the slow ray of the accessory plate, if the colors add, then the mineral has positive elongation. If they subtract, then the mineral has negative elongation. If the colors add, we may also describe the mineral as length slow. If the colors subtract, we may describe it as length fast. Okay, now the next thing I want to do is to demonstrate the use of the quartz wedge to locate the slow direction in a particular mineral grain. And this is a diagram of a quartz wedge. The elements of a quartz wedge. It typically has this sort of shape. In fact, I have a quartz wedge handy here so you can see the particular form of this quartz wedge itself. The quartz wedge is in fact a wedge of quartz. If you looked at it from a side view, you'd see that it's much thinner on the leading edge, the edge that goes first into the microscope, than it is on the far edge. And so the effect of this increasing thickness of quartz within the quartz wedge is that the retardation constantly increases as you insert the quartz wedge. So the difference of this accessory plate from the other two is that this is a dynamic test. That is, that you have to use the quartz wedge, you have to know the sense of motion of the quartz wedge as you insert it into the microscope slot. Now, I want to demonstrate the use of the quartz wedge and the kind of material which the quartz wedge is best used on is the mineral mounts which do not have a constant thickness, in which the interference color actually changes throughout the mounts. And so I'm going to show you a mount of some sand grains. And the sand grains are mounted on the thin section in such a way that the grains themselves are actually thinner on the edge of the grain than they are in the center of the grain. And I can demonstrate this. I can point out to you that the sequence of interference colors that occur from the edge of the grain to the center of the grain is the same sequence that you see on the Michel-Levy chart. Here, for example, is our first order white color, and now we're going into the second order and finally some third order colors in the center of these quartz grains. So that this particular grain then does not show one interference color, but instead shows a whole sequence of interference colors from the center to the outward edge. Now I can measure the location of the slow ray by using the quartz wedge now in the accessory slot. And so I insert the quartz wedge into the accessory slot. Now, what I want you to do is I'm going to switch to the microscopic view here in a section, but in a second. But I want you to keep in mind the motion of the quartz wedge when I say I'm sliding the quartz wedge in. Okay, that's the time when you want to look at the pattern of interference colors. It's during the time that I'm sliding the quartz wedge in, and that means then that the retardation that I'm imposing is increasing all during the time that I'm sliding the quartz wedge in. I also want to call your attention to the fact that this particular quartz wedge has marked on it the position of its slow direction, just like this. So I'm now going to select a particular quartz grain that has increasing interference colors, and we'll look at it now in our cross-polarized light, and we'll be inserting the quartz wedge. Okay, I'm going to pull it out. Now I'll insert it again, insert the quartz wedge, and you can see that the pattern of colors are, for this particular grain, are moving up slope. The colors move from the outside of the grain toward the center of the grain. Okay, the interference colors move from the outside toward the center of the grain as I am inserting the quartz wedge. And now I'll insert the quartz wedge again, and you can see that the colors are sliding in, moving up slope. In this kind of situation where the colors move up slope, we say that the colors are falling. This means that the quartz wedge, the slow direction in the quartz wedge, is opposed to the slow direction in this particular grain. So we can locate again, sometimes very conveniently, the slow ray with using the quartz wedge. Now let me rotate this grain 90 degrees, and I'll show you the same test using the quartz wedge again now on this grain at its illumination position 90 degrees previously. And now you can see that the colors move down slope. They move from the center of the grain toward the outside. And I'm inserting the quartz wedge now, pulling it out, inserting it again, inserting the quartz wedge, and the colors are moving out of the grain down slope. In this kind of situation, we say that the colors rise, that the colors are rising as I insert the quartz wedge, and this is an indication then that the slow ray in this particular mineral grain, this particular quartz grain, is now parallel to the slow ray in the accessory plate. Now the application of the quartz wedge then is particularly important when you see a confusion of interference colors. And the interference colors are variable from the edge, evidently as a function of thickness. It's very easy to locate the slow ray using the quartz wedge. Now finally, as a final set of orthoscopically observed properties, I want to demonstrate what are called some special properties. The first one of these that I want to show you is twinning. And twinning is a crystallographic phenomena where the mineral has a twin plane located in it, and frequently these twin planes show up optically in very dramatic sort of way. To demonstrate this, I have a thin section of an orthosite. An orthosite is a rock, of course, made up virtually entirely of plagioclase. And we're looking now at the plagioclase in cross-polarized light. And as I rotate the stage, you can see, and I'll point out for you specifically the polysynthetic twinning, which is so characteristic of plagioclase. It's this style of twinning, sometimes called albite twinning, which helps us identify plagioclase. And plagioclase, of course, is a very common mineral, in fact the most common mineral in igneous rocks. And twinning is one of the main ways in which we can recognize it, because plagioclase has a very distinctive style of polysynthetic twinning. Other minerals, for example microcline, has another style of twinning which is also highly distinctive and can be used as an identification criteria. Well, another special property can be illustrated in this thin section of granite. This is actually a granite, metamorphosed granite. And this property shows up in the mineral quartz. And we're going to look at the quartz grain now, and I'll point out some of these quartz grains in cross-polarized light so that we can observe its extinction. These quartz grains do not have a simple coherent extinction. Instead, extinction appears to migrate or undulate across the grain. This style of extinction is called undulatory extinction. And it is characteristic of, particularly of quartz in rocks that have been metamorphosed or strained to some degree. And undulatory extinction is characteristic of quartz. Quartz is one of the very few minerals that shows it, and so it can be used as an identification criteria for quartz. Finally, I'm going to look at a thin section of the mineral chlorite. And this is a rock made up virtually entirely of chlorite. If we look at the chlorite in plain polarized light, we can see that it has a distinctly green color. In fact, it's pleochroic in greens. But chlorite looks very unusual in cross-polarized light. Here we're looking at it in cross-polarized light, and you can see that it shows a interference color which you can't find on the interference color charts. Sometimes this color is an abnormal blue, sometimes it's an abnormal brown kind of interference color. But the important point is that these blues and browns, which chlorite exhibits, are not found on the interference color chart. They are truly abnormal interference colors. And chlorite is one of the very few minerals that shows abnormal interference colors, and it's a optical property which we can use to help identify chlorite. Well, in the next tape, now we're going to look at conoscopic view and the additional optical properties which we can describe in uniaxial minerals when looking at them with conoscopic view.